would like to talk about recent progress on Einstein constraints, including questions about asymptotic localization at infinity and the construction of gravitational singularities. We will begin with some elements of Lorentzian geometry and the questions about solving the Einstein equations to define spacetimes of general relativity. But the main focus indeed will be on the constraints, which are equations of Gauss-Kodadzi type related to the local geometry, and we will ask questions about local and global geometry involving low decay or low regularity of solutions. There will be two main topics in the next two videos, and in this video I would like to concentrate on a general background and some elements about the evolution. The first results in the next two videos will be first a joint work with Tika and Wigan about the Einstein equations when you prescribe the asymptotic at infinity, and you look for a geometry that has rather low decay. It's asymptotically flat, but it may have arbitrarily low decay at infinity. The second topic will be, again, a situation where the constraints play a very important role, also in some asymptotic form, as you will see. And we will be discussing scattering maps that are relevant to describe the transition across a singularity hypersurface in a cosmological spacetime. So geometry will be singular, and we will have to revisit the question of junctions that is somehow classical when the spacetime is irregular. At least limits exist on both sides of the singularity, but this won't be the case here. There will be a singularity as you approach a certain hypersurface. This is a joint work with Bruno LeFloch in Paris and Gabriele Veneziano in Geneva. We therefore begin with a background on mathematical general relativity, starting with the notion of Lorentzian four manifold. So it's a manifold with signature minus plus plus plus. And in this setup, we look for solutions to the Einstein equations. So it means a metric, possibly some matter fields, which I will not mention too much in the course of the lecture, but somehow they are part of the problem and they need a specific modeling. And we look for solutions that satisfy a certain initial value problem. The way to prescribe the initial data set is to fix a Riemannian three manifold together with a extrinsic curvature. If you think of this manifold as an hypersurface embedded in the spacetime that you want to construct, you typically need to prescribe the induced metric and the extrinsic curvature. But as I just mentioned, in addition to that, certain matter fields may be necessary depending whether you look at vacuum equations or non-vacuum equations. We will be mostly interested in the constraints that these data must satisfy. So they cannot be arbitrary, but the metric G0, the tensor K0, must satisfy certain equations which are of this form. They involve the scalar curvature of the initial metric. They involve the norm and the trace of the second fundamental form, K0. And so this is the Hamiltonian equation that you produce in this way, and rho 0 would correspond to the mass energy density in your initial data set. And in addition, there is a momentum equation that gives you a constraint on the divergence of K0 as a source term, which is prescribed. It's a momentum of the matter field in the problem. There are a lot of results about stability for these equations, thinking of the evolution problem, but most of them are for vacuum spacetimes. So I mentioned a number of names. The work by Christodoulou Kleinerman is the first pioneering work in this direction concerning Minkowski spacetime. And it was followed in much more recent years by work about the stability of Schwarzschild or Kerr. So these are explicit solutions to the Einstein equations in the vacuum. And proving stability requires a lot of advanced techniques for a nonlinear system of wave equations. Myself, I'm interested in situations where you go beyond Ricci flat solutions and you add some effect of matter, or even if you stay in the vacuum, you would like to go beyond asymptotic symmetry, which is assumed when you talk about perturbation of Minkowski or Schwarzschild spacetime. So we would like to look at solutions that have more broader asymptotic behavior at infinity. And this is one of the issues we will address in this work about the Einstein constraint beyond spherical symmetry. And related to that, there is the issue of if you allow more general initial data set, can you actually propagate globally these initial data sets and think of a result of global perturbation, global nonlinear stability, like I just mentioned for Minkowski or Schwarzschild or Kerr spacetime? And the answer is yes, and this is a joint work with Yuma, which I will also mention in the next few slides. And so I was mentioning my interest to go beyond Ricci flat, beyond asymptotic symmetry. And I'm also interested to go beyond regular solutions, as I told you in this work about cosmological spacetimes and the issue of crossing singularity hypersurfaces. Self-gravitating massive matter field, so really going beyond vacuum, leads you to a very rich and complex global dynamics. And if you want to understand how a matter field evolves in a context of general relativity, you need very sharp estimates about the decay of solutions at time-like infinity, null infinity, and space-like infinity. I return to, I present it here briefly on this slide. So proving the nonlinear stability of such matter fields was done in the past couple of years by Ionescu, Posader, and by myself and Yuma, by two different techniques, two independent proofs, the so-called method of resonances or the so-called Euclidean hyperboloidal foliation method, which is a method I have introduced. So this is a theorem. The outline of the theorem, because the statement takes more than a few lines. What we have done here is to take the Einstein equations coupled to a Klein-Gordon field. So it means that the capital T that you saw on the previous slide has a certain expression, there is a certain model assumption that is made on a matter, and the Bianchi twice contracted Bianchi identities will tell you that this additional matter field has to evolve by a wave equation on the unknown metric. So G is the unknown metric of the problem, phi is some additional unknown. And more precisely, if you want to treat a massive matter field, what you get is in fact a Klein-Gordon equation which has some additional term, m square phi, representing the mass of the matter, of this massive matter model. You prescribe an initial data set, and in addition to G0 and K0, you also add the initial value of this matter field and a quantity representing the time derivative or the velocity, if you wish, of the matter initially. Everything has to be close to Minkowski data, but saying how close it is a big issue which is what I will address in the second video on constructing solution to the constraints. So we will see to appear very low, in fact, decay conditions at space-like infinity. And the result is the fact that the initial value problem admits a global solution, which in this context means that you can construct a space-time which is globally hyperbolic in a certain sense that I'm not going to really discuss here, but you solve these equations, and which are behind is a system of nonlinear wave equations that you will deduce from the Einstein equations in a proper gauge. And in addition to proving that there exists a global solution to the system of PDE, you also need some properties asymptotically in time, which is this property of the space-time that you construct is future causally geodesically complete. So you think of having an observer in the space-time, and this observer can live forever in the space-time. In addition, we will have estimates that say uniformly we stay asymptotically close to Minkowski space-time. So having such a result requires bounds on the decay of solutions in space, in time. And the way we have implemented that in our method was to introduce a foliation that capture both effects. So outside a certain large cone, a wave cone, we use asymptotically Euclidean slices to describe the spacetime. And inside this wave cone, we introduce slices that are asymptotically hyperbolic. And this is a way that we capture the decay, space-like and time-like infinity. But of course, the foliation has to be defined globally. So the two foliations are merged in a vicinity of the wave cone. And part of the analysis is also, so not only to analyze the decay, time-like and space-like infinity, but also to have a very sharp control of what's going on near this light cone. And typically the estimates are much more tricky to establish and even to define, to figure out in the vicinity of this cone. The symmetries of Minkowski space are somehow fundamental in the analysis, but in the case where you want to handle a massive matter field, you cannot use a scaling field of Minkowski space. So doing a scaling would not leave the Klein-Gordon equation invariant, quite the opposite. And the mass term prevents you to use the scaling field, which means that behind there will be norms, Sobolev norms, that are much weaker than if you could use the scaling field as it is always done in previous works on the stability of Minkowski space. So sharp energy estimates, pointwise estimates of weighted Sobolev RD Poincaré type are proven, and the coupling between the nonlinear geometry and the nonlinear matter effects are essential. And in the end, you produce this technique of Euclidean hyperboloidal foliation method, turns out to apply to a broad system of coupled wave and Klein-Gordon equations. So I will not say much more about that, but now let me say a few words about the Einstein constraints. And this is one of the two main results we will be talking about in these 3 lectures. The constraints can be thought of as a nonlinear elliptic system. And so it's really a problem of Riemannian geometry. It's not a standard problem, but it's a problem that can be reduced to techniques of Riemannian geometry. There's a long history, starting with Lichnerovich in France in the 60s. Corvino, Schoen have done very important work, and many other names that I will mention later. And in my work, I relied on a recent contribution by Carlotto and Schoen about a localization at space-time infinity. And so just to give you an idea of what we'll be talking about later, they have a result about localization of space-time infinity. I will explain more what it is later. And in their results, they get a decay, but they are not able to control the effect of terms of 1 over r, and 1 over r is a critical decay that you would see in the expression of the Schwarzschild metric, for instance. So what I've been interested to do here is to revisit the techniques and apply it to, in fact, to a different problem in the end, where I could address questions at the level of harmonic decay that is typical of Schwarzschild. And this was done by relaxing the requirement at infinity, which I believe is physically natural, and introducing this a certain problem of asymptotic localization. So let me say roughly what it is. You take the Einstein constraint equations on a 3-manifold, say with 1 asymptotic end, and you make a decomposition, and I have a picture below to tell you what it is. So you think of decomposing asymptotic infinity into basically 3 regions. There is a region where you want your solution to be asymptotically Euclidean, in a sense that I have specified here. So G is a G Euclidean plus something that decay faster than 1 over r in the Euclidean region. You also would like to have an asymptotic region where your solution is equal to Schwarzschild at a high order, meaning that the additional error, if you like, or decay, is 1 over r to the power q, and this q is strictly bigger than 1. So this is, for me, this asymptotic localization that I can do. I choose to have Minkowski somewhere, some region, Schwarzschild in some other region, and you will see we will have many variants of that. And now what happens in the remaining region? In the remaining region, which is localized between two cones, if you like, what we can prove is that the solution decay like 1 over r. So we do not control, or we actually control and also can say properties of the term 1 over r. But we have a solution that is very well controlled at the 1 over r level, and it includes any ansatz that you would like to prescribe at infinity. So this is the philosophy of this result. We prescribe a seed metric at infinity, and in the case of this specific problem, design seed data with certain free parameters, just the free parameters, and understand the effect of certain mass correctors that will need to be studied by the implicit function theorem. So this is a problem I would like to return to next. And now let me tell you a few words about the second main problem for these lectures, which is this question of bouncing at gravitational singularities. So bouncing cosmology, this is an old problem, but it has not been very well understood, and there's still a lot of progress to be made in this direction. So we think of a space-time that has a singularity hypersurface, and it's typically contracting and then expanding. If you want to go through this singularity hypersurface, there will be an expanding region. And I'm interested in the junction between the contracting and the expanding regions. To do that, we'll need to do some asymptotics near the hypersurface, analyze the behavior, and I will put myself in the behavior called quiescent regime, where the metric has a certain monotone behavior. The dynamics could be more complex, but already looking at this situation of quiescent regime is extremely interesting, I think. We will define certain singularity data. So you approach your singularity hypersurface and you want to characterize. So it's what I call GK phi 0, phi minus plus, phi 1 with a plus or minus subscript are basically the data on the singularity. So you should really think of them as similar to the data that we have put for formulating the initial the constraints, the initial data set. But here it will be singularity data sets. And the question I'm addressing is to look at the constraints for that, but And so to put this GK5051 minus in the set of solutions to the asymptotic constraints. And so having done that, having analyzed these constraints, the issue I want to address is how I can jump moving this data on before the singularity to singularity data after the singularity. So there will be a map. The map, I call it singularity scattering map. And one big issue is what is this map? How do you determine this map? And I will not tell you exactly what this map is, but I will produce a classification of all possible maps under certain conditions, but which we believe are reasonable geometrically or physically. So this is the issue. And the answer in a short way will be that we will discover 3 universal laws of quiescent bouncing cosmology, which we will call first law, second law, third law. And they will have to do with the Kastner exponents, some transformation of the matter that will be pretty simple and geometrically beautiful, and some additional scaling about the direction of some other quantity. So analyzing the asymptotic version of the constraint would be important, and all previous works in this sort of questions were done for symmetric spacetime, spatial junctions that were proposed in the literature. But our strategy is not to make any symmetry assumptions. So we really work without any assumption. I mean, there will be some assumption, but you would see some basically kind of localization conditions we will impose. And this classification gives rise to universal scattering laws or model-dependent scattering laws. And I'm going to discuss that in the third lecture. So let me conclude by now telling you an additional overview for the evolution part. And I would like to show you some constraints. So again, at the end of a few pages here, I will show you some constraints, but the constraint will now be stated for modified gravity. And I think it's an interesting setup. So let me start by telling you about the Einstein gravity model coupled to a Klein-Gordon field. So I'm just writing a little bit more about what I showed you before. We have the wave equation, and we have the Einstein equation. The Ricci curvature is 8 pi nabla phi plus a potential times a metric. So this is a nonlinear geometric system of PDEs. But you can also modify the action that is used to derive the Einstein equations and consider the integral of f of r, where f is not the scalar curvature, capital R, but it's a modification. There are many modifications in the physics literature, but here I'm looking at the case where you add a quadratic term to the scalar curvature. Kappa is thought as a small parameter, so 1 over kappa will appear in some of our estimates, would be a large parameter, and it can be considered as a mass parameter. So it's really an analog of the mass parameter c square that appeared, or I call it m square in a previous slide. It appears in a Klein-Gordon field. And you will understand that in a few minutes for a good reason. So I'm not showing you how you derive it, but if you do the usual derivation of looking at a critical point, you get these equations. So m alpha beta is 8 pi t alpha beta. T alpha beta will be the same matter field contribution to the matter field that you could get before from the Klein-Gordon field, for instance. But on the other hand, the G alpha beta, which was the Einstein tensor, is now replaced by a kind of variant of it. So you have f prime of r, which in fact is something close to 1. So you recognize immediately that m alpha beta is formally close to G alpha beta. And there are corrections. And what's important to realize is that the corrections involve 2 derivatives. We have nabla alpha, nabla beta of a certain nonlinear function of the scalar curvature. So you have actually increased the complexity of your model by 2 additional derivatives. So instead of being a second order system of PDEs for the metric, it is now a fourth order systems. So it seems almost intractable from a PDE point of view, but in fact, and so analyzing the global dynamics seems to be, very, very difficult. But in fact, there is a reduction, and this is this reduction that I want to discuss. Before I do that, I put again a long name of, but not the full list, or just the main names of people who contributed to the question of stability of Minkowski spacetime, because this is indeed the issues that we have addressed with UMA, proving the stability, the global nonlinear stability of Minkowski spacetime with low regularity conditions in space, as I told you already. But we did that in the setup of f of r gravity in the situation where there is this effect of this parameter kappa. So let me spend a little more time now to tell you how this small parameter kappa appears in the field equations of modified gravity. And it comes in the following way. You want to derive a formulation of f of r gravity, which is useful for PDE, for the analysis. And this is how it is done. And it actually goes back to considerations by physicists on reformulating f of r gravity and connecting it to other theories of gravity. So I'm going to introduce a conformal transformation based on the factor kappa rho, where rho will be related to the scalar curvature, like you see in the picture. So if you replace f prime of r by its definition and you expand the log, you see that rho is, you see that rho has a dimension of the scalar curvature in fact. So it's you think of it as a nonlinear function or a certain perturbation of the scalar curvature. So, and now we go from fourth order to third order by doing this conformal transformation, and you see it by looking at the equation below. So the equation below are now formulated for the conformal metric. So GDAG is my new unphysical metric, if you like. So GDAG has the properties that the Ricci curvature is equal now to some additional term plus the contribution of the matter. And the additional tensor, S alpha beta, is related to nabla rho plus f of O. So you can immediately, if you think of quantities I wrote on the previous slides, you see immediately that it looks like the effect of a matter field where f1 of rho would be related to the potential of this matter field, and the rho would be the matter field. So that's basically, you can already see the ideas for the reformulation just by doing this conformal transformation and seeing that rho appears like a matter field in this new formulation. So below I just wrote that when kappa goes to 0, rho converge to the scalar curvature, and we do recover the Einstein field equations, and the contribution from kappa are just gone when kappa is 0. Now, of course, I want to keep the effect of these terms, so I look at the evolution equation of rho. Since rho is considered as a new matter field, that's what I'm doing now. I want to treat rho as an independent field. It's natural to derive an evolution equation and to hope that it will be again a Klein-Gordon equation. And that is indeed the case, but it requires some, to collect the terms in a proper way. And if you do that, this is what you get. So you get 3 kappa box of rho, where the wave operator is evaluated on this unphysical metric GDAG, then minus rho for the contribution of the matter of the Klein-Gordon mass contribution, and then you have certain source terms that are not so important. Before it was 0 if you had a Klein-Gordon equation, but these terms are of high order in the analysis that we will be doing. So what's most important to observe is that we have now a fully second order formulation of modified gravity by doing that, provided we keep the, I call them the defining constraints that tell you how, after you solve for rho in GDAG, you can actually recover the physical metric G. And it's done by just remembering the previous relations between G, GDAG, and rho. And so we have, we could be disappointed in the sense that we have reduced modified gravity to massive gravity in the usual sense. But there is something important here from the analysis or geometric point of view, is that we have done that, but we have done that by keeping a certain parameter in the problem, which I have called kappa. And so we have an additional challenge, which is interesting from the analysis and the geometry point of view, which is the effect of kappa being very small. Physically, it has to be very small. But what really happens when kappa is arbitrarily small? And can we validate the F of R gravity and prove that it is indeed a perturbation or a correction of the usual gravity? So we would like certain estimates that say that when kappa goes to 0, we do converge to the usual Einstein equations, and possibly get some additional estimates to estimate the difference between the solutions. So this is what we have done, and this goes through defining a notion of initial data set for modified gravity, and having a notion of maximal globally hyperbolic F of R Cauchy development. I'm not going to enter into details of that here. Let me emphasize again that the F of R gravity has 2 additional degrees of freedom, which we understand what they are. They are the prescription of the scalar curvature and a time derivative or a Lie derivative in time of the scalar curvature. And there is an important understanding that the so-called constraints, the defining constraints that I mentioned before, can actually be propagated from any given Cauchy hypersurface. So this has to be checked. And of course, the Einstein constraints have this property. If we impose them initially on our initial data set, it will be propagated by the evolution. And then I arrived to something I wanted to show you here. So I want to show you now the Einstein constraints for modified gravity. I wrote them here in a form that is maybe not so compact, but I have simplified to see the structure, but we'll have a more geometric notation later on. I have replaced the scalar curvature on the initial slice for this unphysical metric GDAG. So I have removed the subscript 0 for the initial data and the upper script DAG to tell you that this was stated on the unphysical metric. And so having done that, you can see now the equations where the first equation is really, you recognize the equation I wrote before, but there are some additional effects. The first line comes from basically only the Klein-Gordon field, and it's only the second part that comes from the effect of modified gravity, but it comes in a singular way. And the momentum constraints are also written below, and they look similar. So there's not so much difference at the level of the constraints, and the issue for modified gravity is more an issue of propagation and having a global control on the evolution that is important here. So the singular limit problems that we have solved here is to say that as long as kappa is fixed, you have the same evolution problem as doing the Einstein massive field problem. But when kappa goes to 0, if you want to recover, you need to be able to justify this convergence. For instance, this sort of statement here. And doing that is something that requires a more fine analysis on the dependency of your estimates. So I mentioned Sobolev, Poincaré, Hardy estimates before, or energy estimates. So all these estimates have to be done in a way that is uniform with respect to this parameter K. So that's what we have done, and it leads to a justification of modified gravity, at least a mathematical justification of that. So let me end by saying the next two videos will focus on the constraints. So there will be Riemannian geometry in content. There will be this work on the global analysis of asymptotically flat solutions and the question of localizing the solutions at infinity. And then there will be the question of local analysis of asymptotic solutions on a singularity and how you jump from data, singularity data, on one side of the singularity to the other side of the singularity. So thank you.